Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from homework section 7.2, which is taking a look at the quadratic formula. Now, the quadratic formula basically helps us to solve quadratic equations, and it will work on all types of problems, even problems that are non-factorable. So basically, we'll solve the same types of equations that we're doing with completing the square. And in fact, the formula for the quadratic formula comes from completing the square. And I think I'm going to go ahead and show that to you. I wasn't sure. I was going to save it to the end, see if I had energy for that, but I think we're just going to do it right here at the beginning. Let's just do number one, and then we'll actually run through the algebraic proof on where this formula comes from, which is something that I wouldn't ask on the test, but it's just kind of neat to see where this formula came from. So anyhow, the quadratic formula is this guy right here. So let me go ahead and highlight that. It would be x equals, so when you're solving a quadratic equation, you're going to want to put it in standard form, set it equal to 0. A cannot equal 0, because if a equals 0, then it wouldn't even be a quadratic anymore. But anyhow, you can actually, instead of factoring it or instead of completing the square, you can use this quadratic formula. It gives you the same exact answers. And the quadratic formula, of course, is just right here that I just selected. It's the opposite of b plus or minus the square root of b squared minus 4 times 8 times c all over 2a. And where do these a, b, c's come from? Well, they just come from the coefficients of the quadratic formula when put in standard form. So what I want to do is I want to take a moment, actually a little more than a moment, and show you where this comes from. Let's go ahead and just run through this. Once again, this particular part of proving the quadratic formula will not be on the test, but it's kind of neat to see where it comes from. So you could just kind of watch or fast forward or whatever you're going to do. But anyhow, here's the formula. Let me put the formula up here so we kind of see. Well, first of all, this formula works for quadratics in the form of ax squared plus bx plus c equals 0. And, if it's factorable, that's fine, factor it. But if not, or if it's factorable, either way, you could always get your answers for x by putting in the quadratic formula, which is the opposite of b plus or minus the square root of b squared minus 4 times a times c. This is all over 2 times a. And of course, these variables are coming from the coefficients right here. Okay. So basically what I think happened is someone came up with this great idea of completing the square, and that's what we did last section in 7.1. But I think some smart mathematician probably saw this particular problem and got tired of completing the square. I don't know exactly what how the story goes, but that's what I think happened. Got tired of completing the square and said, let me complete the square one more time in this general formula, in this general form, and when I do that, it'll produce a formula for us. So how do you complete the square with this thing? Well, it's a nightmare. That's why it wasn't done right away. Someone had to really think about it. But how do you complete the square with this thing? Well, first of all, your leading coefficient has to be 1. So now you're going to have to divide by a. Okay, so you divide each term by a. Well, that, of course, cancels down to 1 or reduces to 1. We get x squared plus b over a x. I'm going to subtract this on both sides, okay, which is going to give me a negative c over a on the right side. I'm going to leave a space because what do I need to do? I need to complete the square like we did on the last section. How do I complete the square? I take this term, the linear term, the coefficient in front of the x to the first power, b over a. I cut it in half. Easiest way to do that with a fraction is multiply it by a half. That equals b over 2a. And then I square it. Oops. When I square it, I get b squared over 2 squared, which is 4, a squared, which is a squared. So that is the magical amount. Oops, I guess I'm going to use that color. That completes the square. So I better add that to both sides of the equation. So I'm going to add b squared to both sides. I'm sorry, b squared over 4a squared You can see why this is a little bit of a nightmare. Well, now we are ensured that that's a perfect square because we went through the procedure of completing the square. And of course, don't look very far because it's always going to be right there, right before you squared it. So that's what it factors down to. So x plus b over 2a, quantity squared. And now we need to add, or actually subtract those two. And of course, if you're going to subtract, you must have like or common denominators rather. So what are the common denominators here? Well, they're going to be 4a squared is our least common denominator. Well, my first term is already that, b squared over the LCD 4a squared. However, my second fraction or denominator is missing something. To make the LCD, I need a 4 and I need another a. So I'm going to multiply it. So up top, c times 4 times a, let's just write it as 4a times c. And down below, that gives us 4a squared, which is our LCD. Now I can, in fact, subtract those two, right? Which then gives me b squared minus 4ac all over 4a squared. Now what I want to do is I want to undo the square, right? I'm using the square root property now. Basically, I'm completing the square in the general form, which is really pretty nasty. So I'm going to square root both sides. When I square root both sides, I do not want to forget plus or minus. That leaves me with x plus b over 2a, which equals, up top, plus or minus the square root of b squared minus 4ac all over the square root of 4a squared. Whoops. Something on my screen, sorry. Chasing this. Okay, come on, let's get back to normal. So then, let's see. Up top, I've got plus or minus the square root of b squared minus 4ac. But of course, down here, down below, that is a perfect square. So that comes out as 2a. And I still have this x plus b over 2a. There is something on my screen that's driving me crazy. There we go, got rid of it. So now I want to subtract, right, this on both sides. So I get it to move over to the right. So when I subtract b over 2a on both sides, it disappears on the left. And now I've got negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And you can really see, right, where's the formula? The formula is right here, right, called the quadratic formula, right? And you can see it's starting to take shape. Now, luckily, we already have like terms of denominators, like denominators of 2a. And so all we need to do is just combine them. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And ta-da, that is the quadratic formula. So once again, where does the quadratic formula come from? It's not just some magical thing that just comes to us in the book. Some mathematician at some point in time got pretty clever and said, I'm going to complete the square with this nasty quadratic equation in total general form, right? No, not a constant to be seen anywhere. And they completed the square, and that gave us a whole new formula for us to use. And that's what this whole section 7.2 is all about, using the quadratic formula. So now you know the story. Okay, so now we go over here and we got to use the formula. Don't have a ton of space here, so I think I'm going to work it right over here. So when you take a look at the formula, the first thing you have to really make sure is that you have this in standard form, and you do have it in standard form. That means, you know, we have the x squared first, so 3x squared, and then our next power is x to the first, so negative or minus 4x, and then our constant, set it equal to 0. Now let's identify our a value is 3, our b value is negative 4, and our c value is negative 15. So this is something people do when they're kind of new at using the quadratic formula. If you've done it many times, then you might not write the ABC down and just kind of keep it in your head. Now, of course, we're going to use this quadratic formula. Where is it? It's right here. So take a look at this as I'm doing it. taken x equals, I want the opposite of b, so opposite of negative 4, plus or minus the square root of negative 4 squared, minus 4 times a, which is 3, times c, which is negative 15, all over 2 times a, 2 times 3. Now, what I'd like to do, and I don't have a lot of space this time, but I like to take this interior, the radicand, and simplify that first. Let me go ahead and do that up here. Or maybe I can sneak it over here and work this problem right here. I have negative 4. So let me just, I'm not going to have a lot of space to show a billion steps. But I've got a negative 4 squared. So here I'm right here. Negative 4 squared is going to be 16. Now I'm just going to copy the rest down. Minus 4 times 3 times negative 15. So what I want you to think about here is, think about this as a negative 4. I know it's minus 4. You could also think of it plus a negative 4, but you really need to pay attention to those signs, right? So when you pay attention to the signs, it's going to be negative 4 times 3 times negative 15. And when you multiply all that up, you're going to get a positive, because a negative times a negative, you're going to get a positive 180. And when you have 16 plus 180, you get 196. So let me write down what I have so far. I've done some simplification here. We've got the opposite of negative 4, so positive 4, plus or minus the square root of, positive 196. Now down below we have 2 times 3, which is 6. The nice thing about 196 is it's actually 14 squared. So it is in fact a perfect square. So this is going to be nice, because this guy right here, the square root of 196 is just going to be 14 squared, so it simplifies out to just 14. So now we've got this over 6. So as you can see, we have just all real numbers here. We don't have like the square root of 3 or something like that, right? That doesn't simplify out. So you're going to have two solutions. One solution is going to be obtained by using let's go ahead and use a blue plus. So 4 plus 14 over 6. Well, 4 plus 14 is 18, divided by 6 is 3. So there's a solution. And the other answer is obtained by taking 4 minus 14. Let me use some color on that. 4 minus, there's my minus sign, right? So minus 14. And that is all over 6. Of course, 4 minus 14 is a negative 10 divided by 6. That's going to reduce down to, let me rewrite that. Reduce down to a negative. 2 goes into 10 5 times, and 2 goes into 6 3 times, so negative 5/3. Okay, and there's the solution. Now, something to kind of be aware of, just to tie things together. Whenever you have these numbers, answers like this, these nice rational answers, look at 3, negative 5/3, right? They're not irrational like square root of 7 or square root of 3 or square root of 5. They're not any of those. They're actually rational solutions. That just tells us that this original problem back here at the beginning actually could have, this one right here, actually could have been solved by factoring, right? But right now, they're all into us practicing the quadratic formula, so that's what we're doing. But that was actually factorable, which is probably the most preferred way if it's factorable. Let's try this one right here. And so, of course, we want to know that A equals 1 and B. First of all, make sure it's in standard form, right? So x squared plus x squared minus 7x minus 18 equals 0. That's in standard form. So A equals 1, B equals negative 7, and C equals negative 18. So let's go ahead and use our formula. X equals the opposite of B, so opposite of negative 7. Sometimes we just write 7, right? The opposite of negative 7 is 7. You can just write 7 down. Just trying to show all my little steps here. Plus or minus the square root of negative 7, right? B squared, negative 7 squared, minus 4 times a is 1, times c is negative 18, all over 2 times a, 2 times 1. So like I said before, I want to take this radicand inside and start to work this. So I've got a negative, I'll just write it down, I've got negative 7 squared minus 4 times 1 times negative 18. Okay, well, negative 7 squared is 49. And when I multiply this together, negative 4 times 1 times negative 18, I'm going to get a positive 72. And when I take 49 plus 72, I get a 121. Okay, and that actually should kind of ring a bell for us. We're going to revisit that. I've got a negative, or the opposite of negative 7 is just going to be 7, plus or minus the square root of, what was that, 121? Well, 121 is just 11 squared. So the square root of 121, or 11 squared, is just 11. So now we have 7 plus or minus 11 over 2. And now we're almost there. Once again, I don't see any square roots of 3's or radicands that don't simplify down, that are not perfect squares, right? It was nice because this was nice because we had this perfect square, which just turned into a rational number. And so therefore, our answers are very nice, which means we could have factored it. Let's finish this thing off. We should have 2 solutions, right? We should be getting 7. I'll do this again. 7 plus 11. 7 plus 11 over 2. Which that 7 plus 11 is what? 18 over 2, which is 9. So 9 is one of my solutions. And then the other answer is going to be by using this subtraction symbol. And so we've got 7 minus 11 over 2. 7 minus 11 is negative 4 over 2, which gives me a negative 2. So I get 2 answers, a 9 and negative 2. All right. Solve the quadratic equation by the quadratic formula. Once again, make sure it's in a standard form for that, and it is. I think what I'm going to do is I'm going to go ahead and write up here a equals 4, b equals negative 28, c equals 1. And then I go ahead and just use my quadratic formula. We start by taking the opposite of b, and b is negative 28, plus or minus the square root of b squared. Well, b was negative 28 squared, minus 4 times a, which is 4, times c, which is 1, all over 2 times a, 2 times 4. Just like before, I like to take, oops, that's not what I like to do. Just like before, I like to take this radicand in here and solve it over here, right? So that's going to be negative 28 squared. What is negative 28 squared? I don't know. I got to look that up. Negative 28 squared is a big number, 784. Minus 4 times 4 times 1. So a negative 4 times 4 times 1 is negative 16, or minus 16. And 784 minus 16 is 768. So let's just kind of see what's happening over here. Of course, the opposite of negative 28 is 28 plus or minus the square root of, well, we simplified it down to 768 all over 2 times 4, which is 8. Let's go ahead and take a look, and let's get this a little bit smaller. Boy, that's too small. That the eraser tip is tiny. A little too accurate for my taste. Now, we have this under the square root, right? So, you know, actually it factors down to 256 times 3, which is a perfect square, but you know, I didn't even know that. So so how did I do this? Well, I just, I realized that it was going to be divisible by 2 and maybe 4, right? And so I just kind of started messing around with some numbers. What did I do? I think I divided it by, let me grab a calculator real quick. 768. What if I divide it by 4? So one way to do this is so you just start breaking it down. So divided by 4 is 4 times 192. And I don't know, maybe I can divide by 4 again. Yep, I can. So 48 times 4, and we still have this 4 right here. Now realize that 4 times 4 is a perfect square. So you already have one perfect square there. Are there more? I don't know. What if we divide 48 by 4 again? So now we have a perfect cube. We want perfect squares, not perfect cubes. And this is where you know that 12 is just 3 times 4. So you can see that we have 4 times 4 times 4 times 4. So you can say that's 4 to the 4th power, but we really want a perfect square because remember the index on this is a square root. So why don't you just multiply those and get 16 and multiply those and get 16. Oh, there we go. 16 times 16 is the perfect square, right? And so, you can do this, much quicker if you knew right off the bat that this factors down to 256 times root 3, and you know that the square root of 256 is 16 root 3, right? That'd be the fastest way. But if you didn't know that, you could just do it in a bunch of little steps and get yourself down to the fact that there's your perfect square, 16 times 16. So, if you had, so if I just kind of took a look at this, right, if it was 16 squared times root 3, well, whenever the power matches the index, out comes that base of 16, so that's just going to be 16 root 3. So that was a lot of work, but because I was trying to explain things too. This particular, the square root of 768 just simplifies down to 16 root 3. So now we've got 28 plus or minus 16 root 3 all over 8. So that's all good and everything, but the only thing we need to do now is we need to make sure, do we have anything that we can reduce out? And I'm seeing up top I could factor out a 4, which leaves me with 7 plus or minus. If I factor a 4 here, it's 4 root 3. Down below, 8 can be factored as 4 times 2. And then there we go. Look at that. We've got common 4s that will reduce down. And I'm left with my final answer. And you can put this in. I tried this with MyLab. You could just put it in as 7. And there is a plus or minus button. 4 root 3. And then put it all over 2. And it'll accept that as the perfect answer. Okay? All right, let's take a look at the next one. Now, this one is definitely not in perfect form for us. So what we need to do here is we need to clear the fractions legally. So we're going to multiply both sides by q. So we multiply both sides by q. Let me find a color to work with. So I'm going to multiply this side on the left by q and the right by q. We also know that this q is in the denominator, so we should take a little note here. Q cannot equal 0, right? Okay, and then we can check that in the end. But when we multiply this, what do we end up getting? Well, let's see this. This is going to be q times 3q is 3q squared, and q times the negative 4 is minus 4q. And on the right-hand side, the q's will reduce, leaving a 9. Let's go ahead and put this in standard form, which would just be 3. Well, we should show that I must subtract a 9 on both sides. And when I do that, I get 3q squared minus 4q minus 9 equals 0. I have it in standard form now. If you don't put it in standard form, when you grab your A's, B's, and C's, like for instance, this 9 was positive 9, well, you need to have it in standard form. The C value actually is negative 9, and so your signs will be off. Let's go ahead and write down our A value is 3, our B value is negative 4, and our C value is negative 9. We're ready for our quadratic formula, which is x equals the opposite of b, so opposite of negative 4, plus or minus the square root of b, which is negative 4 squared, minus 4 times a, which is 3, times c, which is negative 9, all over 2 times a, which is 3. As I've done before, I like to take this guy and simplify that out here. And I like to do that. One of the reasons I like to do it is a couple reasons. First of all, students will mess up the order of operations sometimes when they don't do that. And second of all, this thing I'm highlighting in the radicand, this thing I'm highlighting, it actually has a special name, discriminant, that we're going to look at the very end. All right, well, we have negative 4 squared, which is 16, minus 4 times 3 times negative 9. Well, when we multiply all this up here, I end up getting, what do I get? I get negative 4 times 3 times negative 9, which is plus 108. And 108 plus 16 is 124 rather. Okay, so here's what I've got. I've got a negative times a negative, or the opposite of negative 4, which is just 4, plus or minus the square root of this 124. And then this is all over 2 times 3, which is 6. So I'm getting there. Is 124 a perfect square? And I don't think so. And I do believe it's divisible by 4. So I go ahead and I take a look, and it is. Square root of 4, so 4 times 31. So 31 is not a perfect square, but 4 is. So this will simplify down to 2 square root of 31. Now we've got, I'll write this right here because I'm running out of space. We've got 4 plus or minus. Of course, I'm going to replace that with its simplified version, which is 2 square root of 31, and this is all over 6. Well, I see some common factors that are going to be needed, we're going to need to deal with. I've got a common 2 here, so I'm going to factor out 2, which leaves me with 2 plus or minus root 31. If that's a bit confusing, you could always distribute the 2, and we should get the same thing here, right? 4 plus or minus 2 root 31, and we do. And then let's look at the denominator is 6. Of course, 6 is 2 times 3 if you want to do that to highlight that. Cancel or reduce the common 2's, which is going to leave us with our final answer, which is, let me write it this way, x equals 2 plus or minus the square root of 31, and this is all over 3. And that is your final answer, 2 plus or minus square root of 31 over 3. The way that my lab is putting this in is it's putting it actually in using parentheses or braces rather. So it just has you putting it in this kind of thing. And so whenever you put an answer in braces, so this is our final answer right here. I'll do it in green. Whenever you put it in braces like that, you don't say x equals, right? You're just listing the answers. You don't say x equals when you put in braces. All right, solve the quadratic equation by using the quadratic formula. Here we go again, okay? And so I guess what I do want to highlight here is let's look at back at this solution. Okay, back at this solution that we got a final solution of 9 and negative 2, and those are two rational solutions, which means you could have actually solved this problem right here by factoring, okay? But when we see an answer like this, when we see an answer like this that is that shows something that's irrational, and what's doing it is the square root of 3, right? That does not simplify down, and that's irrational. When you see something like that, you know that that original problem, this guy right here, was not factorable. And so the only way you could solve this and solve for x is either use the quadratic formula, which we did, or 7.1, which was complete the square, because it's not factorable. So we got two new techniques that deal with factorable or non-factorable problems, which is awesome, right? And then we did this one right here, and you can see the solution once again. It has this square root. Notice that square root of 31. Well, that's irrational. So once again, the problem that we started with up there, would not be factorable and would not work with that technique. So completing the square or quadratic formula. Number 6, solve by using the quadratic formula. So once again, we're going to want to go ahead and say, well, A, it is in standard form, and we want to say A is 1, B is -4, C is 11, X equals. And so when I usually do this, you do this after a couple times and you realize, okay, it's the opposite, right? It's negative, the opposite, or negative -4. So if it's the opposite -4, I just write down 4. But if you find yourself making mistakes, then don't do that. Also, you know that this -4 is going to be squared, so it's always going to be positive. So you don't really have to have the sign there. And then it's -4 times A, which is 1, times C, which is 11. Couldn't read my own handwriting. 11. And I can't read this one. 11. There we go. Okay, so now down below, it's all over 2 times A, 2 times 1. Just like I've done every single time, I like people to get used to seeing this interior part as something that we can pull out, because that's part of the lesson, something called discriminant. And so you'll be used to that by me doing this every single time. -4 squared is 16, minus 4 times 1 times 11. And I think, yeah, there we go. Okay, this is number 6. So we've got 16, and we've got a -4 times 1 times 11 is -44. And so now we've got 16 minus 44 is -28. So what do we have so far? Well, so far we have 4 plus or minus the square root of this -28. And it is all over 2 times 1 is 2. So tell me about -28. Well, let's put it in under a square root, because that's how it is in our quadratic formula. And is there a perfect square in there? And you get better and better at this stuff. How about 4 times 7, right? Isn't that a perfect square? And then we deal with that negative by having a negative under the radical. We know that's going to be I. We know the square root of 4 is 2, and the square root of 7 doesn't simplify. So we can say that this -28 simplified down to 2 root 7i. So this guy just becomes this new little thing right here. So it's going to be 4 plus or minus 2 root 7i. And make sure, I didn't do a great job there, make sure, and especially when you write it in your solution, make sure that you hit right arrow when you have the 7 cursor under the radical, right arrow, and then this I has to be outside, cannot be under the radical, otherwise it'll be wrong. And it is all over 2. Now you know that we can factor out a 2 up top, so it leaves with a 2 plus or minus root 7i, and then this is all over 2, and so we're going to reduce our common 2's, and it leaves us with, if I'm going to do it as the book does it, actually they have it up top there right here, but I'll just write it here. With braces, you would just write it as 2 plus or minus the square root of 7, right arrow, make sure the I is outside the radical, don't put it under. And there we go. That is our final solution, 2 plus or minus square root of 7i. Good. Okay. And solve the quadratic equation by using quadratic formula. And you got to make sure it's in the proper form, right? So in order to do that, we're going to have to subtract 40z on both sides. That's really a bit too small. But if I zoom in and use a different color, and I subtract 40z on both sides. Well, if I do that, the new thing I have is 25z squared minus 40z plus 18 equals 0. I've got it in the proper form. And that allows me to identify that A equals 25, B equals -40, and C equals 18. Now, if we had a common factor with all three of these, A, B, and C, then we can actually factor it out and make the numbers smaller to work with. That's a trick we can do, but it's not the case here. We do have it in standard form, so we're good to go. Let's go ahead and say X equals, the opposite of -40 is 40, plus or minus the square root of -40 squared, minus 4 times A, which is 25, times c, which is 18, all over 2 times a, which is 25. Once again, we're going to take a look at this radicand. We could call it the discriminant, I think, because that's what we're going to call it real soon here. And we've got negative 40 squared, which gives us 1,600 minus 4 times 25 times 18. Well, let's see, 4 times 25 is 100 times 18, so this is negative 1,800. And when we subtract that, we get negative 200. So you can see that that negative 200 is going to be under the radical symbol. So this is x equals. Well, let's see, how does this simplify down to? How about the square root of 100, square root of 2, and you know what? We can define this as an imaginary number. So this is going to be 10 root 2i. So we replace this right here with this, and now we've got 40 plus or minus 10 root 2i over 50. Now, how do we write, because this is now an imaginary or complex answer, right, with that I there. How do you write complex solutions? Well, we always write them in the form of a plus bi, where a is the real part, and this bi is the imaginary part, right? So we need to break this apart and do that. So this is going to be 40 over 50 is the real part, plus or minus 10 root 2 over 50i is the imaginary part. Of course, you can see some common factors that are going to reduce here, like 10 goes into 40 4 times, and 10 goes into 50 5 times. So that's just going to be 4/5. And then 10 goes into 10 once, and 10 goes into 50 5 times. So it's sort of bugging me right there. Let's rewrite that a little better. So we got 4/5 plus or minus square root of 2 over 5i. And of course, you cannot put those together. This is complex form, where you've got the real and the imaginary part, which do not come together. So that's how you write the solution. And with MyLab, they like to write it as in braces. So that's fine too. So you just do that. Okay, we are almost there. We have a new word called the discriminant. I'm using the same exact color, red, for a reason, because every time I wrote this radicand, I did it in red, right? And that is actually what the discriminant is. That is actually the discriminant. So, and there's a bunch of rules here that helps us. Now, the discriminant is a number that helps us discriminate, which always sounds like a bad word, but it just helps us figure out how many solutions this quadratic equation has. That discriminant does that for us without having to fully solve the problem. Okay, so how do you remember this stuff? Here's how I remember it, just to fill you in how I do it. So I already know the quadratic formula, right? I already know the quadratic formula is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Now the discriminant is just this part right here. So that's really what we're looking at for now. But it also, when we come back and look at the quadratic formula, it helps us understand how many solutions there's going to actually be. And one thing that gives us two solutions is the plus or minus symbol, right? And we can also tell what types of solutions, right? Because if this red discriminant is negative, you know you're going to have an imaginary number. You're going to have two complex solutions. So they give us the different types of solutions over here on the left. But let's go ahead and work this through in our head. So if the discriminant, which is, how do you calculate it? Well, it's b squared minus 4ac. If that is greater than 0, if it's greater than 0, and let's also say if that's greater than 0 and it's a perfect square, greater than 0, and this is a perfect square. What's a perfect square? Like 4, 16, 25, 36, 49, right? It simplifies down, perfect square. If that discriminant is greater than 0 and a perfect square, well, what's going to happen? Well, how many solutions you're going to have? First of all, if this discriminant right here is a perfect square, well, you're still going to have the plus or minus, so you're going to have 2. And if it's a perfect square, it simplifies out. You're going to have 2. What are my options? You're going to have 2 rational solutions, aren't you? 2 rational solutions. Okay, just to kind of give you an idea, if this red thing was bigger than 0 and a perfect square like 16, well, that's going to simplify to 4, and then you're going to be able to add all together using the plus or minus to get 2 answers that are rational solutions. What else could happen? Well, the b squared minus 4ac can still be bigger than 0, so it's positive, right? But what if it's bigger than 0 but not a perfect square? Well, if it's not a perfect square, what's not a perfect square? Like something like, what if that red thing is 3? It's bigger than 0, but it's not a perfect square. Well, that's going to be an irrational number, right? So you're still going to have the plus or minus here. So you're going to get 2 irrational solutions. Well, okay, I think we got when the discriminant is bigger than 0, we got that figured out. What if the discriminant b squared minus 4ac is actually equal to 0? Well, if this guy right here is equal to 0, then it's plus or minus. Well, you can't have plus or minus 0, so then that part goes away, and you're just left with negative b over 2a, which is just going to be, where's my options? 1 repeated real solution. So in this case, you're just going to get 1 repeated real solution. Solution, I don't know, solution, I'll write like that. Okay, let me get rid of some of that stuff, like that. And lastly, what's the last thing we have not taken care of? What if the discriminant b squared minus 4ac is in fact less than 0, so it's a negative? Well, if you think about it, if we have a negative radicand here, what does that look like? When you have a negative radicand, like negative perfect square or not, you're going to get an imaginary solution. An imaginary solution, when it has a real part and imaginary part, you put it together, it's a complex number. So you look over here and you're going to get, this is where you have 2 complex solutions. This is where you get 2 complex solutions. All right, so those are 4 different possibilities. And like I said, if you forget, you can always kind of work it through your head. Wait, it goes under the square root, and so that tells me if it's negative, it's going to be complex with that imaginary number. If it's equal to 0, you're going to not have plus or minus 0, so you're only going to have 1 solution. If it is greater than 0 in a perfect square, well, this simplifies down nicely to get these 2 rational solutions. And if it's not a perfect square, then they're going to be irrational solutions. So hopefully that helped out a little bit. Now let's go ahead and see if we could actually do this problem. So remember, we want the discriminant, which is just b squared minus 4ac. Well, you still have to remember what still needs to be put in standard form, and it is a equals 1, b equals negative 9, and c equals 7. So you go ahead and put those values in. Negative 9 squared minus 4 times a, which is 1, times c, which is 7. So then we get negative 9 squared, which is 81. And then we need to multiply negative 4 times 1 times 7 is minus 28. And 81 minus 28 is 53. Now 53 is greater than 0. So we're in one of these two categories, 1 or 2. And it is not a perfect square, right? 53 is not a perfect square. So the discriminant actually is 53. Let me get rid of some of this stuff. The discriminant is 53. It's not a perfect square, so it must be two irrational solutions. So it's this guy right here. Discriminant is 53, and we get two irrational solutions. Let's do the next one. I don't think we have two more to do here. So it's in standard form, so A equals 5, B equals 7, and C equals 10. So once again, they're asking us to determine the discriminant of the quadratic form of the quadratic equation. Use the value of the discriminant to determine whether the quadratic equation has two real solutions, two irrational solutions, one repeating real solution, or two, wow, what's going on here? Or two complex solutions. Okay, so let's go ahead and do this. Well, remember, b squared minus 4ac. And remember, if you forget what the discriminant is, just go back to your quadratic formula. Oh, there it is. b minus 4ac under the square root symbol. Okay, so it's not hard to remember if you have that quadratic formula memorized. So b, in our case here, b equals 7. So we've got 7 squared minus 4 times a, which is 5, times c, which is 10. 7 squared is 49. And then we've got 49. We've got the negative 4 times 5 times 10, which gives us a negative 200. 49 minus 200 will give us a negative 151. And so that's our discriminant, negative 151. By the way, negative 151 is less than 0. So it's negative under the radical. That's got to be the complex part, right? With the imaginary. So it's got to be A, which is two complex solutions. Okay, let's finish her off here. Determine, same thing. It's in standard form. So A equals 4, B equals negative 20, and C equals 25. So now we go ahead and once again, b squared minus 4ac is called our discriminant. We put in a negative 20 for b, minus 4 times a, which is 4, times c, which is 25. Whoops, this is negative 20 squared. Well, negative 20 squared is positive 400. And when we multiply negative 4 times 25, we're actually going to get 400. Hey, look at that. 400 minus 400 is 0. And 0 equals 0. Which case is that? Well, if you forget, you could remember the quadratic formula, which says opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Well, you just found out that what was this under the radical? It is a 0. And the square root of 0 is 0. And you can't have a plus or minus 0, so this goes away and this goes away. And so you just get one repeated real solution. So first of all, the value of the discriminant is 0. Second of all, how many solutions? One repeated real solution is what we're going to get. Okay, and that does it for this little adventure of mathematics. This is that was the last question. I hope that helped out. I hope everybody's doing great. Take care, and I'll talk to you soon. Bye.